Welcome to Copilot Podcasts. Picture a surface with only one side and one edge, and to travel across its entire face and return to where you started, you have to rotate not 360 degrees, but a full 720. And when you layer prime numbers and color-coded force fields onto that surface, something genuinely strange happens. Hidden geometric symmetries start to appear out of nowhere. Today, we're doing a deep audio dive into the former KT prime Möbius visualization, what its translucent grayscale surface actually represents, why the vector fields are color-graded, and what those 20 zero points are telling us about the hidden structure of mathematics. By the end of this episode, you'll understand the topology behind the Möbius strip, how prime numbers connect to geometric turning points, and why this visualization is more than just a pretty shape. I've got someone here who lives and breathes this stuff, so let's get into it. Walk me through.
So the foundation of everything here is the Möbius strip itself. According to Wikipedia, it's a surface that can be formed by taking a rectangular strip and giving it a half twist before joining the ends. And the key property, the one that makes it so mathematically wild, is that it is non-orientable. That means within the surface, you cannot consistently distinguish clockwise from counterclockwise turns.
Wait, you can't tell clockwise from counterclockwise? How does that even work?
Right, so imagine you're an ant walking along the surface. You start on what feels like the top. You keep walking in a straight line, and eventually, without ever crossing an edge, you end up on what feels like the bottom. And then you keep going, and you're back where you started. The surface has only one side. That half twist scrambles your sense of orientation completely.
And that's why it takes 720 degrees, 2 full rotations, to complete the traversal?
Exactly. The half twist means that a single 360-degree rotation brings you back to the same point on the surface, but flipped. You need to go around twice, 720 degrees, or 4 ni radians, to genuinely return to your original orientation. That's where the 4 ni in the name comes from.
Okay, that's actually a really clean explanation. And this thing has been around for a while, right? Like, mathematically speaking?
It was formally described as a mathematical object in 1858 by Johann Benedict Listing and August Ferdinand Möbius. But here's the part that kind of blows my mind. According to Wikipedia, the shape had already appeared in Roman mosaics from the 3rd century CE. So ancient artists were drawing this thing more than 1,000 years before mathematicians gave it a name.
That is wild. Like, were they just stumbling onto topology by accident?
That's the question, isn't it? It suggests there's something visually and aesthetically compelling about the shape that humans have been drawn to for millennia, even without the formal mathematics to describe it.
And it's still showing up everywhere. I mean, the recycling symbol, that's a Möbius strip, right?
Yes, and according to Wikipedia, the list goes further than that. MC Escher's artworks, the design of the NASCAR Hall of Fame building, even some molecular structures. The shape keeps reappearing because its properties are genuinely useful, not just decorative.
Okay, so we've got the strip itself, but the visualization we're talking about isn't just a Möbius strip, it's a Möbius transformation visualization. Are those the same thing?
Great distinction. They're related but different. The Möbius strip is the physical surface, the twisted band. A Möbius transformation is a mathematical function. According to Wikipedia, it's a rational function of one complex variable of the form where you have 4 complex coefficients, and the key constraint is that AD minus BC is not equal to 0.
Okay, I'm going to need you to make that less abstract for me.
Sure. Geometrically, what a Möbius transformation does is this. You take the complex plane, you project it onto a sphere, that's called the Riemann sphere, you move and rotate that sphere to a new position, and then you project it back down to the plane. And the remarkable thing is that this process preserves angles. Every straight line maps to either a line or a circle. Every circle maps to either a circle or a line.
So it's like a very specific kind of distortion that keeps the local geometry intact even while it's reshaping the global picture.
That's a really good way to put it. And all Möbius transformations together form what's called the Möbius group. Technically, the projective linear group PGL2C. According to Wikipedia, this group is isomorphic to the group of orientation-preserving isometries of hyperbolic 3 space. So it's not just a visual trick, it's a fundamental symmetry group in mathematics.
And this connects to physics too, doesn't it? I feel like I've heard something about this and relativity.
Yes, and this is one of those places where the math gets genuinely surprising. According to Wikipedia, the identity component of the Lorentz group, which governs special relativity, acts on the celestial sphere in exactly the same way that the Möbius group acts on the Riemann sphere. These two groups are isomorphic. So an observer accelerating to relativistic velocities would actually see the pattern of constellations in the sky continuously transforming according to infinitesimal Möbius transformations.
Wait, so if you were traveling near the speed of light, the stars would rearrange themselves according to Möbius geometry?
That's exactly what the mathematics says. And Wikipedia notes that this observation is often taken as the starting point of twistor theory, which is a whole framework in theoretical physics. So the visualization we're talking about isn't just abstract art, it's touching something real about how the universe is structured.
Okay, I want to get into the visual layers now. The grayscale surface, the vector fields, the prime markers. Let's start with the surface itself. Why grayscale? Why translucent?
The translucency is actually doing real mathematical work. Because the Möbius strip is non-orientable, it has only one side. If you render it as an opaque surface, you lose information. You can only see one face at a time. But with a translucent grayscale surface, you can see through it and observe how the vector fields and prime markers interact across the entire structure simultaneously.
Oh, that's clever. The transparency is compensating for the fact that the surface doesn't have a conventional inside and outside.
Exactly. And the grayscale keeps the surface visually neutral so that the color-graded vector fields can carry the informational weight without competing with the surface color.
So let's talk about those vector fields. What is a vector field for someone who hasn't thought about this since high school calculus?
A vector field assigns a vector, basically an arrow with a direction and a magnitude, to every point in space. According to GetZenQuery's vector field documentation, in 2 dimensions you can represent it as f of x and y equals p of x and y in the x direction plus q of x and y in the y direction. So at every single point on the surface, there's an arrow telling you something about the behavior of the field at that location.
And the color grading is what makes those arrows readable at a glance?
Right. According to the GGV fields documentation, which is a vector field visualization package, the standard approach is to map the norm of each vector to color. The norm is just the magnitude, calculated as the square root of u squared plus v squared. So a low magnitude vector gets one color, a high magnitude vector gets another, and you can immediately read the intensity of the field across the whole surface without having to measure individual arrows.
So the color isn't decorative, it's encoding actual mathematical data.
Completely. And the vector field also carries information about divergence and curl. According to getZenQuery, divergence measures source and sink strength, whether the field is spreading out or converging, and curl measures rotation strength. A positive curl means counterclockwise rotation, a negative curl means clockwise. All of that is embedded in the color-graded arrows.
Okay, now I want to get to the part that I think is the most surprising, the prime ring markers. What are primes doing on a Möbius surface?
This is where it gets genuinely deep. There's a paper by Harvard mathematician Oliver Knill titled On Primes, Graphs, and Cohomology that makes a remarkable connection. He shows that the counting function on natural numbers defines a discrete Morse-Smale complex, essentially a mathematical landscape with peaks and valleys, and the Poincaré-Hopf indices at the critical points of that landscape correspond to the values of the Möbius function.
Okay, I need you to unpack that. What's the Möbius function in this context?
The Möbius function is a number-theoretic function that takes values of +1, -1, or 0, depending on the prime factorization of an integer. And what Knill's paper shows is that these values can be read as topological indices. They tell you whether a point in the mathematical landscape is a local minimum, a local maximum, or a saddle point. And crucially, the Morse inequalities in his framework link the prime counting functions to cohomological properties of graphs.
So primes are literally marking topological turning points in the mathematical landscape.
That's exactly what the Harvard paper argues. Knill writes that substantial topological changes happen at square-free integers, and primes are the simplest square-free integers, while harmless homotopy deformations take place at the other points. So the prime ring markers in the visualization are flagging the locations where the topology of the underlying mathematical structure actually changes character.
That's a completely different way of thinking about prime numbers, not just as numbers that can't be divided, but as geometric events.
And Knill connects this to the Mertens function, which is the cumulative sum of Möbius function values, by showing that the Euler characteristic of the Morse filtration equals 1 minus the Mertens function. So the global topology of the graph is directly encoded in the distribution of primes. It's a bridge between number theory and topology that runs right through the Möbius function.
And then there are the 20 0 points. What are those?
The 0 points are the locations where the Möbius function takes the value 0, which happens when an integer has a squared prime factor. In Knill's framework, these are the points where the topological index is 0, meaning no change in the Euler characteristic occurs there. On the visualization, they mark the places where the mathematical landscape is, in a sense, topologically inert.
So they're like the quiet spots in an otherwise turbulent field.
That's a good image. And when you plot 20 of them on the Möbius surface, something interesting happens. They reveal a pattern. Because the surface is non-orientable and requires 720 degrees to traverse, the 0 points that appear on what looks like one side of the surface are actually connected to points on the other apparent side. The symmetry only becomes visible when you account for the full 4 rotation.
So the hidden geometric symmetries in the title, those are the symmetries that only emerge when you take the non-orientability seriously.
Exactly. And there's research that supports this idea of symmetry detection on Möbius-type surfaces. A 2010 paper from the Symposium on Geometry Processing by Vladimir Kim, Yaron Lipman, Xiaobai Chen, and Thomas Funkhauser showed that Möbius transformations can detect global intrinsic symmetries in 3D surface meshes. Their approach works by finding critical points of the average geodesic distance function, and those critical points are symmetry invariant.
So symmetry isn't just something you see, it's something you can compute and locate precisely.
That's the key insight from that paper. They tested it across 220 models in 11 shape classes and found an 83% correspondence rate overall. The algorithm finds symmetries that a human eye might miss because it's working from the geometry of distances across the surface, not from visual appearance.
And that's essentially what the 0 points in the visualization are doing. They're the computed locations of symmetry, not just decorative markers.
Right. And the fact that there are 20 of them is significant because on a surface that requires 720 degrees to traverse, you'd expect symmetry points to come in pairs that are separated by exactly 360 degrees of rotation. So 20 points means 10 pairs, each pair connected by the half twist of the strip.
I want to go back to the parameterization for a second, because I think it helps ground all of this. How is the Möbius strip actually described mathematically?
According to the Möbius strip visualization documentation from thinkingsmith.com, the standard parameterization uses two variables, u and v. The x-coordinate is 1 plus v times cosine of u over 2, all times cosine of u. The y-coordinate is the same bracket times sine of u, and the z-coordinate is v times sine of u over 2. The variable u runs from 0 to 2 mundi, and v runs from -1 to 1.
And that u over 2 in the cosine and sine terms, that's what creates the half twist?
Exactly. When u goes from 0 to 2 mundi, one full loop around, the u over 2 term only goes from 0 to 1/0, which is a half rotation. That's the half twist built directly into the equations. And it means that when you complete one loop, the surface has flipped, which is why you need to go around again to get back to your original orientation.
That's such a clean way to encode something so counterintuitive into a formula.
And the visualization tools that render this, like the Python-based Möbius strip visualizer on GitHub using NumPy and Matplotlib, calculate the surface area using partial derivatives and vector cross products. So even the rendering process is doing calculus on the surface.
Let me ask you something that I think listeners might be wondering. Is there a risk that this kind of visualization, beautiful as it is more aesthetic than informative? Like, are we learning something real, or are we just making math look cool?
That's a fair challenge. And I think the answer is that the best mathematical visualizations are doing both simultaneously, and the two aren't in conflict. The color-graded vector fields aren't decorative, they're encoding divergence and curl data. The prime ring markers aren't decorative, they're flagging topological events. The translucency isn't decorative, it's compensating for the non-orientability of the surface.
So every visual choice is load-bearing.
Every single one. And there's a practical dimension to this too. The GeoGebra implementation of Möbius transformations lets you move sliders to see different transformations and their corresponding projections in real time. That interactivity is what turns a static formula into genuine intuition. You can feel how the transformation behaves before you can formally prove anything about it.
That's actually a really important point about how people learn mathematics. The visualization isn't replacing the rigor, it's building the intuition that makes the rigor accessible.
And that's been the philosophy behind tools like Desmos and GeoGebra: graph functions, plot points, visualize, algebraic equations, add sliders, animate graphs. The interactivity is the point. You're not just reading about a Möbius transformation, you're watching it happen and developing a feel for what it does.
Let me bring up one more layer of this that I find fascinating: the connection to Möbius geometry as a whole framework. Because we've been talking about the strip and the transformation, but there's a broader geometric system here, right?
Yes. According to the Institute for Mathematik at Humboldt University, Möbius geometry coincides with the conformal geometry of the n-sphere with respect to its standard metric. And the Möbius group is isomorphic to the pseudo-orthogonal group O, 1, n plus 1, which is the group that leaves a pseudo-Euclidean scalar product of index 1 invariant. These are sometimes called Minkowski spaces.
So Möbius geometry and Minkowski space, the geometry of special relativity, are connected at a deep structural level.
They share the same algebraic skeleton. And that's why the visualization isn't just a mathematical curiosity, it's a window into the geometric structure that underlies both pure mathematics and theoretical physics. The Möbius group plays an important role in the theory of Riemann surfaces, in hyperbolic three-manifolds, and in the Lorentz group of special relativity.
So when you step back from all of this, the surface, the vector fields, the primes, the 0 points, here's what this really comes down to.
The 4-me KT prime Möbius visualization is a convergence of three distinct mathematical worlds. You have topology, the non-orientable surface that requires 720 degrees to traverse. You have number theory, the prime ring markers that flag topological turning points according to Oliver Knill's Harvard research connecting the Möbius function to Poincaré-Hopf indices. And you have field mathematics, the color-graded vector fields that encode divergence, curl, and magnitude across every point on the surface.
And the 20 0 points are where all three of those worlds intersect. The places where the topology is inert, the prime structure is 0, and the field behavior can be read most clearly.
Exactly. And the hidden geometric symmetries that the visualization reveals are only visible because of the non-orientability. On a conventional orientable surface, those symmetries would be split across two separate sides. On the Möbius surface, they're unified, but you have to go all the way around twice to see the full picture.
Which is a pretty good metaphor for mathematics in general, honestly. The full picture is always there, you just have to be willing to go around twice.
And the research from the 2010 Symposium on Geometry Processing makes that concrete symmetry detection on Möbius-type surfaces isn't just visual intuition. It's a computable, measurable property. Kim, Lippmann, Chen, and Funkhauser showed you can find it algorithmically by locating critical points of the average geodesic distance function. The symmetry is real, and it's findable.
So the actionable takeaway here, if you're someone who works with mathematical visualization, or you're just someone who wants to understand what these kinds of images are actually communicating, is that every visual element is a data channel. The color is data, the transparency is data, the markers are data, nothing is decoration.
And if you want to start exploring this yourself, tools like GeoGebra let you interact with Möbius transformations directly, move sliders, watch the projections change, build intuition before you tackle the formal mathematics. And for vector fields specifically, the GGV fields package in R maps the norm to color automatically, so you can start visualizing field behavior with just a few lines of code.
That's a genuinely accessible entry point. You don't need to understand pseudo-orthogonal groups to start playing with this.
Not at all. The visualization is designed to build the intuition that eventually makes the formal mathematics feel inevitable rather than arbitrary. That's the whole point of making it visual and interactive.
And I think that's what makes the 4-me DKT prime Möbius visualization so compelling as an object. It's not just showing you a shape, it's showing you a conversation between topology, number theory, and physics, all happening simultaneously on a surface that refuses to have two sides.
And the fact that it appeared in Roman mosaics before anyone had the mathematics to describe it suggests that humans have always sensed something important about this shape, even when they couldn't say what it was.
We've been circling this idea the whole episode, pun absolutely intended, that the most interesting mathematical structures are the ones that hide their full nature until you commit to going all the way around. The Möbius strip started as a papercraft curiosity in 1858. It ended up embedded in the mathematics of special relativity, prime number theory, and symmetry detection in 3D meshes.
And the visualization makes all of that legible at once. That's the real achievement, not just that the mathematics is deep, but that someone figured out how to make the depth visible.
The surface that has only one side turns out to be the perfect canvas for showing that mathematics itself has hidden sides, and you need to go all the way around, twice, to see them. That's it for today's episode of Copilot Podcasts. If this one made your brain do a half twist, that means it worked.